Our topic today is increasing and decreasing functions and the first derivative test. So, kind of to clear up a misconception that I had, so maybe you'll have. The first derivative test. It's not like the first, then the second, then the third, not an order of tests. This is the first one. But there's a test about that uses the first derivative. Okay, so this isn't the first of many, it's the first of two. If you think about it, it's the first derivative test and then the second derivative test. But it's not first in a series of tests. It's a test that uses the first derivative. This corresponds to section 4.3 in our textbook. So looking at increasing, decreasing functions. Now in algebra, we have the definition for this. That if x sub 1 is less than x sub 2, that implies f of x sub 1 is less than f of x sub 2. That is increasing behavior. So if your inputs are lesser than greater, your outputs are going to be lesser than greater as you go left to right. Decreasing, the opposite. So lesser than greater implies greater than lesser. So as you go left to right, your y values go down, they decrease. Now, this definition kind of leaves itself open to a little bit of ambiguity, I think, because a value where the behavior changes, like this point right here, that point is the right endpoint of a decreasing interval. It's also the left endpoint of a constant interval. And the definition says that point could be like part of both, which I think is weird. So that's our definition. Okay? Our test for this, and the test uses calculus, says rather than looking at inputs and outputs, look at derivative values. If your derivative is greater than 0 in an open interval, then it's increasing in the open interval. If your derivative is less than 0 in an open interval, then you're decreasing on the closed interval. And if your derivative is 0, then your function is constant on the closed interval. Now I think this still has a little ambiguity because we look at derivative values in the open, which you have to, but then you make a determination in the closed interval. So an endpoint of an increasing interval could be the endpoint of a decreasing interval, and the closed interval would include them in both. So like here, this endpoint right here, endpoint of an increasing interval, then the function goes down. Well, in this open interval, our derivative is greater than 0, so we're increasing in the closed from a to b. Say a to b. But then in this interval, our derivative is less than 0 in that open interval, so then we're decreasing from b to c. And b and c is part of both. To me, that's a little ambiguous, like it should only be one. Which one is it? Okay? So this is one of those gray areas in the College Board grading system where the test says increasing, decreasing constant and the closed interval, but they'll accept open intervals. And I always default to the open interval unless something in the problem tells me to report the closed. Okay, so usually I do an open interval, but based upon the wording might lead me to do a closed, okay? So let's look at how this works. We are finding open intervals. So in this case, they're telling us use parentheses. On which f(x) is increasing or decreasing. So increasing or decreasing, we're going to use f prime of x. We're going to use the test for increasing, decreasing, and then justify your answer. These three words. What does it mean in the context of this problem? In this problem, your justification could be a table where you do an interval test, okay? So we're going to use f prime. So f prime of x is 3x squared minus 3x. Go ahead, do a little GCF. And set the derivative equal to 0, kind of those two steps at once. So factor out 3x and x minus 1. So then you have a factor, now 0 product property. And x equals 0 and 1. And those are our critical numbers. Remember, critical numbers, where the derivative equals 0 or the derivative is undefined, critical numbers could produce maximums, minimums. Okay, every max or min is a critical number. Not every critical number is the max or min. Okay, gotta keep that straight. So now we have our critical numbers. Those become the boundaries of our test intervals. So we have 0, we have 1. Going to make an interval table. So x equals 0 and x equals 1. So then, those are your boundaries. Between your boundaries, outside your boundaries, choose easy numbers to work with, okay? So any number less than 0, but choose an easy one. So I'm going to choose negative 1. Negative 1, pretty easy to work with, okay? And then plug negative 1 into your derivative. My advice in this problem, plug it into the factored derivative. Right there. Because we're only interested in whether the derivative is positive or negative. We don't care what the number is, we only really care about the sign, okay? So f prime of negative 1, if you plug that into 3x, so 3 times negative 1, that's negative. Plug it into the parentheses, so negative 1 minus 1, that's also negative. So overall, that's a positive value, which means up to x equals 0 for negative infinity, up to x equals 0, we have increasing behavior. So this is kind of like what we did in trig and precalc, identifying increasing, decreasing intervals. But in trig precalc, we had graphs. Now we only need the equation and its derivative. So choose a number between 0 and 1, do the same thing. So choose an easy number to work with. Let's go 1/2. So now f prime of 1/2. Plug that into the factored derivative. So 3 times 1/2, that's a positive. 1/2 minus 1, that's a negative. Overall, we have negative, so we have decreasing behavior. Now do it again for a number greater than 1. But choosing these numbers, don't choose like 97. Nothing against 97, but it's easier to use 2, I think. So f prime of 2, plug that into the factored. So 3 times 2, positive. 2 minus 1, positive. So overall, that is a positive interval. That is increasing behavior. So then the table kind of gives you visually what's happening. This function is increasing, then the 0 is decreasing, then the 1 is increasing again. So looking at the we're only identifying increasing, decreasing intervals. But looking at the table, you can kind of get an idea of maximums and minimums also, because you see the arrow directions and the changes in the zeros. So this table, kind of a 1-2 punch, okay? You can use it to identify increasing, decreasing, constant intervals. But then if you do your work correctly and you leave yourself the visual trail of breadcrumbs, you can then also use it to see visually about extrema, maximum, minimum intervals, okay? So do yourself a favor. All that work is your justification, and it gives you a good bang for your buck, okay? So f(x) increasing, negative infinity to 0 and 1 to infinity, it's decreasing from 0 to 1 using open intervals. The table is our justification, okay? So kind of some written out guidelines for finding intervals. In the, right here, the strictly monotonic, just that vocab. Knowing what that means. Okay, strictly monotonic means you have only one behavior on the entire interval. So you're either increasing all the time or decreasing all the time. For example, f(x) equals x cubed. There is kind of that leveling off, but that leveling off at 0 you could include in the increasing interval. And then that table really becomes your first derivative test, looking at changes in behavior. If f prime changes from negative to positive, we have a relative minimum. If it changes from positive to negative, we have a relative maximum. If it does not change, you have neither. So every relative maximum is a critical number. Not every critical number is a relative maximum. So visually looking, you see, can they have up, then down, then up. So you see the change in behavior there. So looking at some examples. Oh no, trig, don't get scared, okay? We're only looking at an interval of 0 to 2 pi, the unit circle. And even though it's trig, do the same thing. Derivative first, factor it out, find your critical numbers, make a table. So f prime is 1/2 minus sine x. Derivative of sine is cosine, so minus cosine x. So then set equal to 0. Solve for x, so 1/2 equals cosine of x. And x is, let's see, Cosine is the x coordinate, so when it's x, 1/2 on the unit circle, so that's pi over 3, and I think 5 pi over 3 also, in the first and fourth quadrants. So you have two boundaries, make a table. X is pi over 3 the first time. X is 5 pi over 3 the second time. And choose numbers to the left of pi over 3, between pi over 3 and 5 pi over 3, and to the right of 5 pi over 3. Choose the numbers, plug those numbers into the derivative, and see if you have positive or negatives to look at increasing and decreasing. Where you see behavior changes is where you're going to have your extrema values. Okay, so look at A, B, and C. Check those as my completed notes. One more quick thing. Curve sketching. Sketch a possible graph. We don't have enough information to make an exact graph, but make a possible one. So we know f of 0 is -5, so f of 0, -5, so 1, 2, 3, 4, 5. Still highlighting, oops. Let's change that, 1, 2, 3, 4, 5. There we go, got that. F of 2 is -2, so f2, -2. Alright. And then they say f prime x is less than 0, so f prime is negative, so the function's decreasing. For x less than 0, so decreasing, and x greater than 2, so 1, 2, decreasing. And f prime is greater than 0, so positive, increasing from 0 to 2, so in that little interval, increasing. So based upon that information, make a possible sketch. Remember, you can only make a possible sketch. We don't know yet whether that is exactly how it looks. Okay, we're kind of halfway there to making accurate graphs. We'll get all the way there later. Right now, only making a possible one. So do that, check what you have against what I have. They won't be identical, but they should be similar enough.